Think about it. And this is not a displacement time now, it's a velocity time. So from our previous displacement, I want you to look at Finbar and his graph. Did the gradient of his line change in A? Okay. What do we think? Who thinks the gradient of his line changed? Hands up. Who thinks his gradient stayed constant? What do we think that means? What do you think that means? Yep, okay. His velocity stayed constant. So, how long did his velocity stay constant for? 60 seconds. And what was his velocity? How would we represent that? So, what was his velocity at 60 seconds? 5? What was his velocity at 30 seconds? What about 45? What about 15? What about 5.3? Okay, so the point I'm trying to make is his velocity should be represented by a straight line there. Happy with that? Between 60 and 90 seconds, we go into section B. What was Finbar the Fantastic's velocity in the B? 0. Did his velocity change for that period of time? So we're going to draw a line on the 0 and we connect them. Yes, good question. Then what do we do? Section C. Finbar the Fantastic's velocity in section C was?
Negative 3.33 meters per second.
Did that change throughout the whole of section C? Didn't change it. So what do I expect to see here? Straight line at negative 3.33 across to 180. Do I know what happened after 180?
No.
So I can't write anything for that.
You've got arrow.
No, that's fine there. Alex the Awesome. How is his graph different? I'm going to do it in red. How will we represent Alex the Awesome? You don't need to work it out. Think about it. How would Alex the Awesome's graph look?
Can we do it on this as well?
Yeah, do it on the same graph. Yep. Don't redraw your graph. How fast did Alex the Awesome travel in section D? Same as Finbar, but how did he do it, Brenda? How long did he do it for? 120 seconds. So what would I do? I'd have my red line over with until I got to 120. Then what happened? Was it 120? Yes, it was. Then what happens? So does that look like this? Do I do that? Why not?
It's negative because it's going close to the top.
But that's a negative gradient, isn't it?
Getting close to the top.
We know it's wrong, but we can't explain why.
It'd go vertically down.
It'd go vertically down. So it'd be a straight, because his velocity instantaneously changes to become negative. So down at negative 1.6, a little dot. What's going to happen there?
Just going to go straight to 180.
It's going to go straight until 180. It is a weird graph. Now, I'm going to ask you to do something as a challenge. I want you to find, I'm going to call this little a, actually, I'm not going to call it capital A. I want you to find the area of little a I'm going to put a dotted line here. I want you to find the area of little c. I want you to find the area of little d. And I want you to find the area of little e. And then what I want you to do is area 1 equals A plus C. Area 2 equals D plus E. Okay? Remember our area equation. What's area for, we've got, what type of shapes have we got here? Rectangles. Area of a shape of a rectangle is? Yep, width times length. Just have a crack, see how you go.